Hello, everyone. So this week we have lots to get to. So I'm going to try and keep each section a little bit short and sweet. I tried to sort of cut down everything and sort of just give us the basics of what we're going to need to do these kinds of problems and to really have an understanding of what's going on in these sections. So we're going to talk about solution sets of linear systems, so types of solution sets. I know we already talked about types of solutions, but now we're going to talk about, we'll talk about them some more. We're going to talk about linear independence. We're going to talk a little bit about linear transformations. Hopefully you got a chance to watch that 3 blue, 2, 1 brown video on linear transformations. Honestly, he's probably going to do a better job explaining it than I am, but we'll get there. And then we're going to get into some matrix operations, and that's where we sort of start to get into what I think of as, well, okay, I love the row operations, but our matrix operations tend to be sort of really fun. And that's where we're going to start getting into other ways to solve things. Anyway, before we actually get into our solution sets, we kind of need to backtrack just a little bit. So last week we talked about matrix equations, and we talked about, so those were equations of the form AX equals B, right? So X represented our, there's our solution vector or our variable vector. This is just some other vector that it's equal to. We'll talk a little bit more about ways to define that today. But what we didn't talk about is how to actually compute this. So what do we do? How do I actually get A times X, that X vector? So we did kind of go backwards. So we took vector equation format and used that to find AX. So we're just going to kind of quickly go through this and talk about how to actually multiply these two things together. This is going to help us when we come to talking about multiplication of matrices. So the first thing we're going to do is we're going to rewrite this product into vector equation format, which means I'm going to take x1 and I'm going to treat each of the columns of A as a separate vector. So I have 2, -1, 6. x2 is 3, 5, -2. And x3 times 4, -3, 8. Right, so these are equivalent forms of that expression, and we kind of talked about this last week. So next we're going to compute our scalar multiplication, which means I'm just going to multiply my x1s into each of these vectors. So my new vector, I get 2x1, -x1, and 6x1, plus this vector is 3x2, 5x2, and -2x2. And lastly, we have the vector 4x3, -3x3, and 8x3. And now all I'm going to do is I'm going to apply that idea of adding the vectors together, right? So I'm going to add these together to get a single vector as opposed to these 3 separate vectors. So what I get is I have 2x1 plus 3x2 plus 4x3. Now, it looks like there's a lot going on there, but this is a single entry into this vector. Then we've got -x plus 5x1 plus 5x2 minus 3x3. Again, this is a single entry, so this is still a vector that's going to have 3 entries in it. So you'll notice that each of these vectors has 3 entries, so they're in R3, R3, R3. And so all that means, right, is that I have, so this is real numbers with 3 entries, is really all that means. Now, these, we'll get to that. We're going to just roll with it. All right, so 6x1 minus 2x2 plus 8x3. And this is the result of A times that x vector. Now we have a shortcut, so we don't have to do each step here. We don't have to put it in a vector equation format and then multiply the scalars and then do the addition. Our shortcut is, and these my words here, I struggled with how to actually put this into words. But what we're going to do is we're going to multiply each corresponding position in the columns, in the rows of the matrix by the term in each row of the vector. And our new position or new value is the sum of those products. So right here, if we think about this, so here's the first row, and by corresponding positions, I mean this position corresponds to this row, this position corresponds to this row, this position corresponds to this row. Hard to put into words, but that's kind of what I mean there. And then we're going to go with that. So our result is always going to be a vector. So our result is a vector with the same number of rows as columns in A. Oh my goodness, spelling is, we're having some trouble today. M-N-S-N-A. Oh boy. Okay. Now, another important idea here, so I put a little star here to remind you that for the row vector rule, you have to have, so your vector needs the same number of rows as columns in A, right? So if I had an extra column here in A, I'd have a number here hanging out without a variable. So I need to make sure that those things match. So the number of columns, so notice here this is a 3x3 matrix, and this is a 3x1 matrix, right? So there's 3 rows, 1 column, and you'll notice that these numbers have to match up here. So that's important. And now we can apply this idea to multiplying a matrix by a vector, even if that vector is not an x1, x2, x3, even if it's not variables, if it's just numbers. So we're going to do an example of that really quickly, and then that's sort of it for and some properties. But that's it for my. Hey, I probably should have talked about this last week. So here's our example. So all we're going to do. So this is going to be a new vector, and I don't like how, there we go. Okay, so our new vector, so notice this is a 2x3 vector, this is a 3x1 vector, so our new vector is actually only going to have 2 terms. And so here's what we're going to do, so we're going to take 1 times 4 plus 2 times 3, right, I'm going to match that up with this one, plus -1 times 7, that's in my top position. And the bottom position, so I guess it would help if I highlighted. So this guy and this guy gives me this guy. This guy and this guy will give me this guy. So 0 times 4, and then we have -5 times 3, and 3 times 7. If we simplify this, we should get the vector 3, 6. I sure hope so. If I did my arithmetic correctly, then yes. If not, well, email me, tell me I did it wrong. Cool. So some properties of our vector matrix product, just to sort of keep these in mind, is, and these are actually going to be helpful in a few minutes, or in the next couple of sections, when we start to talk about linear transformations. But so this first one says that if I have the product of 2 vectors, and then, or not product, if I take the product of the sum of 2 vectors, one way or the other, I can distribute that matrix to the 2 vectors and it will come out to the same sum. So whether I sum the vectors first and then multiply by the matrix, or multiply each matrix by the vector and then sum it, I'll come out to be the same thing. Same thing if I take a scalar multiple times either my vector first or do the product of my matrix and my vector and then multiply it by the scalar, I get the same thing. Hopefully that kind of makes sense. If you're really itching to prove that this is true, pick yourself a couple of vectors and matrices and do the fun addition and multiplication and see if you end up with the same stuff. All right, come back and we'll talk about solution sets.